To summarize each of the representations that we've talked about for graphs, adjacency matrix, list of edges, and adjacency list, I produced here this handy table. So let's consider that we write an add edge method. It turns out that this will be theta1 for all of these different representations. The adjacency method will be theta v for the adjacency matrix, theta e for list of edges, and constant time for the adjacency list. And these two we just talked about. This is one you'd have to think about a little more on your own. So this is non-obvious, but it's, if you think about it, the natural answer. These are core pieces of the Graph API, but we can also consider other operations we might add. So we might write another class that tries to, for example, print out the graph, like this code. So print graph we just showed would be theta v squared for an adjacency matrix. It'd be v plus e for an adjacency list, as we saw on the previous slide, and it would just be theta e for the list of edges representation. Likewise, we could write something that says, does a graph possess an edge between s and t? So in this case, with an adjacency matrix, it'd be theta1. We could just go and index directly into the matrix, assuming that we had access to its instance variables. List of edges, we would actually have to iterate through all the edges to see if it exists. And with the adjacency list, if we want to know if there exists an edge between, say, 0 and 2, we have to iterate through this list. And if we store it as a list, as opposed to, say, a binary search tree or something, then in the worst case, it would be theta degree of v. In other words, the length of the list. In terms of the amount of space used, the amount of space for an adjacency matrix is v squared, e for list of edges, and adjacency lists will be e plus v, which is the same thing, by the way, as v plus e, and I may as well just, I'm showing it to you for both because you'll see both used. Okay. Now again, one of the big takeaways here is that this runtime, this theta v plus e, is a very common idea and something I want you to get comfortable with. The study guide questions for this lecture are a great way to do that because we'll see this time and time again. So in practice, if we look at all this, we can get kind of a sense of the trade-offs that are involved. And we can see that, or I'll say that, in practice, adjacency lists are the most common. And one of the reasons is that, at least for our graph implementation, because these are the core operations in the graph, so many of our operations will rely on this adjacency method here. And so that, since it's theta1, that's part of the reason why this is super common. It's also nice because it doesn't use a ton of space. And in a sense, basically, most graphs are sparse. That is, there's not many edges in each bucket. It's not going to be like for each edge there are n over 10 edges. Generally, it'll be some small number, maybe a constant. And so we can kind of draw inspiration from hash tables, right? Hash tables have this interesting property that every single list is short, so we can think of every operation as constant time. And so too with graphs, because graphs tend to be sparse, those bins, those buckets, those lists of edges will generally be pretty short. And so this ends up being a much more efficient representation than either of these two approaches for sparse graphs. Although arguably list of edges can be faster for some certain subproblems. And so if we want to look at what does a graph actually look like, were we to sit down and implement it, it'll look a little like this. So a graph has an integer v. It is fixed. It has a number of vertices that never changes. We have a list of, we have an array of lists of integers. So for each of these lists, for each vertex, we have a list that is all of the adjacent vertices. And when we create a graph, this vertex number v is set. It's fixed in stone forever. Here we create our adjacency lists, and then we just go through and set them all equal to an empty list. That's what this code does. Now again, you might decide that for your purposes, this v should not be constant, but for simplicity, for the sake of a pure, beautiful lecture, we're going to make that strange step. Adding edge is pretty simple, and this is for an undirected graph. So what we'll do is we'll simply say, okay, if we're adding an edge between 0 and 3, let's say, we'll make sure that 3 gets added to 0's adjacency list, and that 0 gets added to 3's adjacency list, and we're good to go. And then this adjacency method here, we'll simply return edge v. And then, as a result, once we have that code, we can then write code like this, and this will print out our graph beautifully, convincing us that we've actually built a graph. So that's it as far as the basic implementation goes. So from here, let's start considering some of these more challenging problems we might want to do, rather than just listing off all the edges.